Very first, we from Leica Biosystems would like to thank Dr. Rajesh sir and also Jipmar for giving us an opportunity to come and share our expertise. I would be taking the fundamentals of microscopy as the topic given to us. Here, it's like sir has laid a strong platform before I present. So there are many things which I would be revolving around the topics what sir just now has talked. So possibly we might think some of the analogies starting from using the spectacles, the magnifying glasses. While we are driving on the streets, when do we feel eyes are strained in the night? Why is that we are not able to see towards sun? Is it the eclipse is not allowed to see, or is it the sun is not allowed to see? Some kind of similar analogies are something we need to think of while or before we are discussing fundamentals in microscopy. With this, I will just take ahead this presentation, and the agenda for this presentation is discussing about microscope, the anatomy of microscopes, the optics involved, optical parts in microscope, different types of contrasts, that is bright field, polarization, phase contrast, fluorescence, and applications of microscopy. The term microscope evolves from a Greek alphabet, Greek words, that is micros, which is equivalent to small, and scope, which means to see. So it's a combination of seeing smaller things which normally we cannot see with naked eyes. And microscope is an equipment which helps us to visualize, to see the small objects which we cannot see with the naked eyes. And microscopy is the field of using microscope to see the smaller organisms, or let us say objects. When we talk about small things, there are different equipments also to see the objects which we cannot see with naked eyes. So microscopy, it helps us to see anything which is having the size of 0.1 micron. To that extent we can see with microscope. Even lesser than that can be seen, but those will be electron microscopes and others. So in short, if it is animal cell, RBCs, mitochondria, bacteria, these kind of things we can visualize with the help of microscopes. Maybe the contrast type will be different in each of them. Live cell will be seen differently than the histopathology cells or something like that. Just to go ahead, I would just like to discuss few things. What is the simple and compound microscope? Simple microscope, or when we use simple microscope, we can consider as the loop which is used by goldsmiths or jewelers to see what is the quality of the jewel, or let us say magnifying glass which is used by watchmakers. These are all simple microscopes. So simple microscope is nothing but one single lens which is helping you to magnify an object is called a simple microscope. When does a simple microscope gets converted to compound microscope is if there is an equipment which has multiple lenses together working, so that ultimately it is enhancing the magnification and resolution in a particular object. That is where it is called as compound microscope. So simple magnification helps to magnify to an extent 250 to 300 times, whereas with compound microscope we can go till 200 times of the size with proper magnification. So a little anatomy of microscope we would like to just share. This is the initial microscopes, which is a monocular. So some of the parts of this microscope are eyepiece, tube, the mirror or the light source, the base, objective, which is the most important thing just now sir also discussed. We will be getting a little more depth into that. This is a similar microscope, but it is not as old as the earlier. The anatomy is little different considering the optical components and the structure of the microscope. This is also a monocular. This is another microscope which is binocular. So the difference between the earlier ones what I showed and this, it helps. Earlier microscope will be like seen by only one eye. Here it is to be seen by both the eyes. There are few other things like how does an eyepiece will be different in different microscopes. One of the part, sir also asked us to discuss the parameters based on which how we need to select the parts of the complete microscope. So when we talk about eyepieces, there are different field of views you can have with particular eyepiece. So some of the eyepieces will be giving you 18 field of view. Some of them will give you 20, 22, 25. There are ranges. So based on this also you need to figure out what microscope you will be utilizing or what microscope will be useful and what should be the field of view. So some of the eyepieces come up with diopters, pointers. If I am using a microscope for teaching purpose and I am using a multi-headed microscope, I will use pointer to help the other people on the other tubes to visualize the objects. Diopters and glass wearer. So if I am a glass wearer, the eyepiece will help me. Some of the specific eyepieces will give me capability. Even if I am wearing the glass, I don't need to take off the glass. So that feature is there into the eyepieces. The next thing is tubes. Tubes are of multiple kinds. So there are some standard tubes wherein there are features like while you are moving the stage on the right side, you actually see or visualize the object is moving in the microscope towards the left side. So it is inverse. So some of the specific tubes are also available which are called image erecting tubes. So you need to know or you need to understand what is the type of tube I should have into the microscope. There are tubes, standard tubes are there, erecting tubes are there. Ergonomic tubes also are available. What is ergonomic tube is like the design of the tube is made based on the structure, posture of human body. So if I am little heighted and the same microscope is also to be used by someone who is little lesser in the height. So there are tubes which can give you capability to tilt the tube. So that is an ergonomic feature which we can use. There are binocular tubes, there are monocular tubes also, there are trinocular tubes also. Monocular is used for one eye, binocular is for two eyes, trinocular 2 eyes plus 1 camera. The third thing, the objective which happens to be the most important optical component of the microscope. So some of the objectives can be used for only bright field, some other contrast type like phase contrast. We need to have a different specific type of objective for that because the structure of that objective has to be different than the bright field objective. Then the stages also. If we are using polarization, into polarization the stage has to be rotating one. So standard stage need not be rotating. You just can move the sample onto the stage on X and Y axis. But in polarization, why is that needed? I'll discuss while we are discussing the polarization. But in polarization, the stage has to be moved. Like it has to rotate. Mirror and light. Earlier days mirrors were used for light source. Now lights are being used. Now just not one source of light, kind of source of light is used. There are multiple sources of light. Yesterday sir was also telling that we need to discuss about the theories as to sometimes it happens that light is creating a strain on my eyes while I am using more hours of microscope. So this could be similar. Just now I was talking that why do we feel strained when we are driving in the night or when a big vehicle is there in front? So because that is something we need to also think into microscopy. There are certain optics which will obstruct that extra light. Sometimes like somebody may have a preference to have reading in the bulb light which is little yellowish. Somebody will prefer in the sunlight and somebody will prefer in LED or white light. It is again preference wise also. So there are ways to convert the sunlight into yellowish light like the bulb looks like. There are ways to convert the bulb like yellowish light to sunlight kind. That is called filters, daylight filters we call, yellow filters we call. These are the things which we need to think of while we are using the microscopes also and the features as well. Just now sir also talked about the magnification. It is just the ratio between the apparent size and true size. Magnification, like the apparent size, if that is becoming more than the actual size, it is called as magnification. Then what is true size? If I am looking at an object from 25 centimeter distance, that is something we can call it as a true size. Like if I hold an object very close to my eye, it may seem very big for me, and if I keep it too farther, it may look like very smaller to me. But what is the ideal thing? It has to be 25 centimeters farther from my eyes, and that is where I need to count whether it is relatively smaller or bigger. Resolution. The shortest distance between 2 points, when we are looking, if there is a distance between 2 points, the smaller the distance, the better is the resolution. And for having better resolution, the classes of objectives, as sir was also talking, we have different kinds of objectives. More the resolution, for sure, more the magnification capability of the objective, better resolution will be there. But at the same time, even apart from magnification, there are few other parameters like numerical aperture. That is something which we will discuss in depth, how to have better resolution with different types of objectives also. When we talk about resolution can be easily described with the help of airy discs. So this is nothing but the light coming from the microscope and the 2 points being diffracted. Here we can see unresolved objects. So these are unresolved objects. These are resolved objects. So here there is no distance between each of them. So here the resolution is lesser. Here the resolution is better. So these are the airy discs. So you can see these are the points. So if this point is more broader to the base, that means the resolution is less. In the further slides also I will be describing. These are airy disc patterns to visualize the resolution. So the numerical aperture is a physical property of optical component. It can be with objective. Here we will consider objective. It can be there for condenser also. So what is this? So it's the physical property to carry the light, and what happens here is this is my distance. This is my distance from the specimen to the objective. That is called working distance. Here, as I am increasing the numerical aperture, as I am increasing the objective magnification, the working distance is getting reduced. You can compare here. So the keeping D and lowering the working distance leads to higher resolution, higher numerical aperture. So what happens when is my numerical aperture more? You can see this distance is bigger, and this, even though the distance, if you look, it is uniform possibly, but the angle between both of them, if you will see, it is varying. The distance D might be uniform, but the angle at which it is opened, more light is being projected towards the objective. That is something called as numerical aperture. You could see here it is more, here the angle is less, and that is what stands to be as numerical aperture. It is the capability of the optics to get into more light. So we just saw numerical aperture only for objective, but here we will see in comparison with condenser, two of the numerical apertures, how they are matching, whether it is lesser or higher. In that cases, how the numerical aperture will give the different contrast is something we would like to discuss here. So you could see here, this is the numerical aperture for condenser, and this little less darker is numerical aperture for condenser, objective. What's happening here is, the numerical aperture for condenser is greater than numerical aperture of objective. In this case, this is something we are achieving, this contrast. Here what is happening, we are keeping numerical aperture both, whether it is objective and whether it is for condenser, both of them are approximately same. The angle between both of them is same. So we are getting a little better resolution here. The third thing is, the numerical aperture for condenser is lesser than the numerical aperture for the objective. Here you can see the difference between the contrast types. Now we need to understand which contrast will help me for me to visualize the object is something we need to think. Sometimes this could be helpful, sometimes this could be helpful, sometimes this could be also helpful. And we can change this with the help of condensers also. Comparing powers of magnification. So what happens is like, if I am seeing something at 7x and something at 10x, 10x is the power, the magnification, multiple number of times. So 10x means 10 times, 7x means 7 times. So what happens when I am using lesser power? I can see more of the structure, more of the field, but not more details. So if I go for higher magnifications, I could see more details, but I am not able to see complete structure. So here I am seeing the bird from all the complete face is seen. Over on the second side, the face is getting reduced. Means details are more, but the field is available less. Image magnification principle. So whether the image what we are seeing, is it real? Is it a virtual? Is it erect? Is it inverse? That is something we will be discussing here. So this is the normal principle, considering the principal axis, the optical center and focus. What happens if my image is, if a body, if the specimen is present here, farther from the principal axis, what happens? The rays of light which are going from this side, the parallel ones go and hit the convex lens, and when they hit the convex lens, they deviate towards the focus side. Every single ray will go as long as they are not from center. If they are in the optical center, they don't deviate, they just go straight. This is the principle of light propagating through the convex lens. So what happens? The place where the deviated lines and the place where the straight lines from optical center meet, that is the place where the object is formed. So here the object is formed here at position B dash. But this will be an inverse image. This is not the real image. This is an inverse image. Similarly, what happens here is, my distance between this optical center to the specimen, it is getting reduced here. As it is getting decreased, you can see this B size is increasing. So as I am coming closer to the optical center, my size is getting increased. But still it is an inverse. It is not erected one. Third example is, I still come closer. When I still come closer, the phenomenon changes. It will not form on this direction in an inverse way, but this is a virtual image formation, and it is in the opposite side. These are principles of image formation with the help of lenses. And this is how, on that principle, the microscope works. So the first, what happens, this particular object is seen with the help of this convex lens, which is present in the objective, and the image is formed this one. So this is upside down, here it is the inverse of that, and now this particular image object, now ideally this is my object, I am seeing this as an object, this is the one which has formed here. Now this particular virtual image is being seen by this particular lens which is present in this. Now with the help of this, I am able to see this in this direction. It is the way up, it is not upside down, it is a virtual image. Some components which are useful into the microscope. This is actually the most important component, that is the objective, as sir also has shared the details. What happens normally, every single objective has lot of details inscribed onto the objective. So this itself is telling my 50x, it means it can magnify till 50x, and also the numerical aperture for this is 0.80. It is PL flutar, it is a type of objective. There are different types. I will just go ahead with the next slides, within the next slides. What's happening here is, the condenser also has to be matched. So there is a color coding in Leica Biosystems. We follow this color coding. So 100x will be all white color, 63 and 80x will be dark blue, lesser than that will be light blue. So here you can see this is 50x. This color is matched here. Now while I am seeing in the microscope, I need to make sure while I am using this objective, I should turn my condenser to this level. This is how only then the numerical aperture of the condenser and the numerical aperture of objective is balanced. The ones which we were discussing earlier, I showed 3 contrasts. That is how this is balanced with the help of this knob. So what is objective and objective types, if we will see? Objective is nothing but there are multiple glass components inside, and they are placed in such a way that the capability of microscope is achieved properly. If I am using this particular objective and the airy disc, you can see this is the airy disc, it is little broader to the bottom. This is an N-plane objective. Here what happens is this is a combination of these blue glass pieces. So this objective is formed with the help of these many glasses, 1, 2, 3, 4, some 4 or 5 odd. And it is being resolved in this way. The airy disc is shown in this way. Now second example is I am using the same 20x, but here it was 40x, here it is 50x. Now see, the airy disc is becoming little thin, means it is resolving little better. But at the same time, the glass components in the objectives are more here, means the complexity of making this objective is being increasing. The third one, again it is 20x, but you see the difference is 80x, 50x, 0.8, 0.5, 0.40 numerical aperture. Here it is better resolution. At the same time you see the complexity. So when I am going towards more complexity or more glass used objective, it is giving me better resolution. It is not just resolution. There are some things, some more parameters called as plane correction. What is plane? If a square is there, if plane is not corrected, it may seem like a barrel for visualization. That is something plane correction. Color corrections are also there. 2 color correction, 2.5 color correction. So what happens? Little difference in the color. So it's like as sir also told, our field is of more of ladies and they differentiate better colors. So possibly for male, like for me at least, green color is green color, but green will be little green, little green, little more green. Those kind of colors can be differentiated by the fraternity here. These are the types of objective. You can see here, this is N-plan, this is PL flutar, this is apochromatic. Something like H-plan is one more category. As we move from H-plan to N-plan to flutar to apochromatic, the image quality enhances, means the resolution enhances, and so is the price also with the objectives. That is the most price sensitive or most pricey component of the microscope. If we see the optical parts in microscope, you can see here this is a compound microscope, a high-end microscope, that is clinical microscope. In earlier microscopes, I could just show here the source of light and it was just getting entered from here itself. But these are some more optics here. So these are the optics which will help for us to have better visualization of the objects. It will not give more strain if these all are the components involved. Gray light, green light, those kind of filters are there. So this is having more filters here while the light is coming also. So good light, bad light can be converted from these optics. This is one path that is for bright field. There is one more light path. Here it is fluorescence. I can just show you. This is how a bright field microscope occurs. Bright field microscope is vastly used. It is mostly used, in fact. Bright field microscope is used more than any other microscope, I can say. So what happens in a bright field microscope? Some of the microscope start the light from here itself, and some start from here. There are different microscopes. For more complex microscopes, the light starts from here. So for an example, if I am using multi-headed microscope, 20 people or 10 people are seeing the objects at one part of time, then I need to have bigger light source so that the light gets divided equally to all the 10, 20 multiple users. So this is a 100-watt light source which is kept at the back of the microscope, and then with the help of even when it is 100-watt microscope, again the one who is seeing here has to be balanced. It should not happen that the one who is on the microscope will have more of the light and his eyes will pain, and the rest of the people will have balanced light. That complexity also is reduced with the help of filters. So light enters here from the condenser, it goes through the specimen, then enters into the objective, then comes to the tube, and from tube, if it is only binocular, it goes to eyes. If it is trinocular, it goes to camera also. We can decide whether all the light has to go to camera or partially it has to go to each, or all the light has to go to binocular also. There are modes, there are mediums through which we can operate into. The the difference between here and here, this is one optical path and this is the second optical path. The microscope is same. The same microscope is featured with two different optical paths, light paths. So this is having a fluorescence light source here. This is bright field light source. In bright field, what happens? The light passes through the objective, whereas this is incident. So light comes from here, gets placed onto the specimen, then from here again the other light gets reflected from the specimen because of the fluoropores, and then this is captured through the camera or through the eyes. We will get more details here. Before we get into some more things, this is one more principle we will have to tell while we are discussing microscopy. There are certain objects, type of objects. This is a normal wave in which light passes. So this has two ways or two units we can say. One is lambda, which is the wavelength, and second one is amplitude. We measure the light in these two units, that is wavelength and amplitude. So here you can say is the wavelength for each part of this wave is uniform. Uniform between start to end of the wave, and the crest and troughs, that is amplitude. What happens? Certain objects are there with the help of, like, if the wave is passed through a particular object, if this object is of a particular kind called as amplitude object, then the change in amplitude occurs. And secondly, there are certain other objects, this kind of object, if the same light, if the same wavelength light is passed through this particular object, the difference here, it was into the amplitude, it has changed the structure. In the height it has changed, but here it has changed into the breadth. You can see the wavelength from here to here the distance, and from here to here the distance, it has reduced. So this has retarded the phase, it has reduced the amplification. So every single object, when it is placed in the microscope, either it will change the amplitude, the height of the wave, or it will change the breadth of the wave, that is wavelength. So technically we need to understand when is this used. In bright field, most of the times this particular phenomenon is working. This is because the light is reduced. So let us say there is something which is clear, that is just glass, and something which is placed on the glass. Just because of that hindrance, there is lesser light coming to the eyes, to the objective, and that is where it is reducing the amplitude, and that is where it is creating the contrast. But there are certain ways to change the, and our normally our eyes will not be able to distinguish between this and this, because it is very minimal. With the help of phase objects, the change in the phase of the light wave is very minimal in normal scenario. No matter which object is that, it is very minimal. We have to convert this minimal change to more change so that the phase contrast can be achieved. That is where. This is for bright field, this is for phase contrast. There is one more thing called as polarization. These are the some of the important principles. If you are keen, then have some research onto this, or maybe if you give some more opportunities for us to engage with you all in your classroom sessions or something, we can share more information on that. This is the bright field microscopy. What happens here is, this is my slide and specimen. If I say, the background always is all bright, because light is coming from the bottom, specimen is in the mid, and then it is seen through the top. Field is bright, that is why it is called bright field. So the complete field is bright. The object which we are interested is dark. These are microbes, and these objects act as an amplitude object. Amplitude object is something which creates the change in the the specimen is dark. Amplitude itself is changed with the help of these objects, and that is why they are called as the objects which are called as amplitude objects. They change in the amplification. So normally, why everywhere we don't use bright field microscopy? The reason behind that is, in some cases, we also have to keep the specimen in live state. With the help of bright field microscopy, we have to stain the specimen. Here, what has happened is, we have stained this into HNE. That is why it is looking this color. So when we are converting this. Initially, when the specimen comes, it has no stain. But some of the stains, like chlorophyll in plants, has already a stain which is little greenish. For that, it doesn't need to be stained. But normally, other specimens have to be stained. And many of the stains are also toxic. They may kill the cells also. And to avoid those scenarios, we don't stain. And when the stains are not done, when the staining is not done, then we'll have to use not bright field, but we have to use some another contrast type, which can be phase contrast or maybe DIC or polarization. Those kind of things we have to see. So some of the stains used are methylene blue for cell nuclei, gram stain for bacteria. These are some of the stains which normally are used. The second type is polarization. The first type, bright field, which is used for stain specimens always. The polarization is the one which is used as a second contrast type, which we are discussing. What is polarization? Is like when the light propagates. It propagates in one direction, but it has two components with that. That is, a wave is in electric field and also magnetic field. So this yellow oscillation is magnetic field. This blue oscillation is electric field. So when we take the magnetic field out, that is not of our interest. Our area of interest is electric field. This would look, so this yellowish is magnetic field if we see in a section, and this bluish is electric field. When we negate or when we take off the magnetic field, the wave would look like this, which is a pure transverse wave, and this will be like this if we see the section. So this looks like plus, and this is just like a line. If we have multiple such sources, like multiple such planes while the light is propagating, multiple such planes will look like this. And if we resolve them in two directions, then the same light will be seen again as a plus. So what happens? Every single light, this light, sunlight, every single light is unpolarized because the plane of propagation are multiple, and they are always perpendicular to the direction of the ray of light. So we have this unpolarized light in multiple planes. We have resolved it for our understanding in lesser planes, that is two planes. Both of them are unpolarized. They are like this light, they are like sunlight, and every single light. All of them are unpolarized. What we will do is, with the help of polarization, we are converting unpolarized light to polarized light. What is polarization? Many of you or many of us are normally using sunglasses with polarization. That is the same mechanism. We normally say polarized light glasses are good for eyes. The similar fashion we are using this polarization contrast in microscope also. And what is that we are doing here is, we are just considering light propagating in one single plane into the contrast creation. So this is how, if unpolarized light, this is unpolarized light, I have resolved it in only two planes. If I see from the sectional side, this would be looking like this. This is this one, and this is just seen as a dot. What happens? If I pass this through a particular crystal structure, what is this? This is a glass component, optics, which is used for polarization, which is having a principle called as bifringence. So what is bifringence is, if a component which has two refractive indexes within the crystal, then it is called birefringence. So whenever the specimen is crystalline, that is where we are using this polarization. So what happens into this bifringence component, this particular crystal, it will allow only one single plane of light to be propagated. Now, these all three are all unpolarized light, but when the unpolarized light passes through this gives the output. This negates this. This particular object will not allow this dots, means horizontally placed unpolarized lights. They will be always propagating parallelly to the axis of this crystallographic axis. So all the lights which are parallel to this are propagating, but not this. You could see this. Now what happens if I place this as a polarization? There is one more component which is similar. The same object, second object is placed perpendicular to this axis, then you can see nothing is passing after that. One is analyzer, the second one is polarizer. These are same components. One acts as a polarizer, second acts as an analyzer. If I place this in perpendicular, they are not acting anything. And this is why we use the rotating stages for polarization to be impactful. So now when we see polarizer and analyzer are together placed in microscope, nothing is coming out. But at the same time, when immediately I place a crystal or the specimen which is bifringence, which is having a property of bifringence, it is giving me again the lights which is again unpolarized. When this unpolarized light passes through this crystal, it is giving these lights. So all those which are horizontally placed are coming out of these optics. This principle is called polarization, and it gives good contrast also. The same thing is also shown here. This is unpolarized lights. So you can see the multiple waves in all directions. Only one wave is passing through this, and when this component, polarization component, is in perpendicular to this, nothing is being passed. So the moment I bring my specimen inside this, in between this path, I can see something out of the path coming. And this is one important feature, and this is to be used only when the specimens are crystalline. I need to understand what are my specimen types also. That is how microscopy is based on. First thing, the specimen has to be stained for bright field. For second thing, it is for polarization, it has to be crystalline in structure. The third thing is phase contrast. The first contrast type, that is bright field contrast type, we were able to visualize the change between the amplitude with the help of amplitude objects, but we are not able to see any change which is naturally occurring in the phase, the unit of phase. If there is any change in the phase of the wave, we are not able to notice with eye, because whenever there is a phase change, it is very minimal, wherein our eyes will not be in a position to notice that. With the help of phase contrast, what we are doing is, we are retarding the light rays, and what we are doing, we are converting these light rays into constructive interference and destructive interference. So what happens, if there is a specimen in between here in the light path, we actually have two components, that is annular and phase plate. With the help of phase plate, what is happening, the light is passing through this white circle inside, and only one kind of phase is getting penetrated. Earlier it was one plane in polarization. There will be multiple waves, but they all were in one plane, propagating in one particular plane, like this way, not like one this and one this, not that way. Here what is happening, they can be unpolarized also, they can be in multiple planes, but they have to have one single phase of light. The phase or the wavelength has to be same. So it sends only one particular kind of wavelength into the specimen. In specimen, what happens, my nuclei will look like different than the membrane, or that will be different than cytoplasm. So nucleus, cytoplasm, membrane or any other granular will have different refractive index, and because of this refractive index, the light coming out of nuclei, the light coming out of the cytoplasm or from the membrane, even if the light which is going inside is all common, but the light which is coming out of all these, we are not just talking about cell, we are bifurcating the cell again. How is the nuclei, how is the cytoplasm, how is the membrane? So based on that also, the light coming as an output of this is changing. So because of this, what is happening is, there is a change between the light which is coming out of the specimen. You could see this is one type of light and this is one type of light. The one which is not going through the specimen, let us say from glass, it is directly going and it is shown in this way. And the one which is going through the specimen is shown as a dotted line. So here what happens, with the help of this phase plate, when we pass these lights through phase plate, that is where one phase, this is one phase and this is the another phase. If they are similar, the phases gets added, and if they are different, then they get negated to each other. And here, within these dotted lines, this phase is created. Within this continuous line, this phase is created. Destructive and constructive phases are formed, and that is where a noticeable phase difference is occurring, and that can be noticed by eye. Naturally, if there is any phase difference occurring, that is very minimal, which will not be able to be noticed by eye. But with the help of phase contrast technique, what we are doing is, we are creating the phase difference between the lights emerging out of the specimen in such a way that eyes can notice with the help of these objects. And this is how you can see. This is one without the phase contrast, and this is with phase contrast. It is having more details and the contrast here. That is the difference. The third microscopy or the contrast type is fluorescence microscopy. One important thing which we need to understand here is there is something called as fluoropore, or we use term called as probes into microscopy. What probes do, or what happens to probe? Whenever there is a light getting incident onto a probe, the atoms into these probes, what happens? The light is a source of energy for them. They absorb the light, they get energized. Once they get energized, they become unbalanced. The atoms get unbalanced and they move to the next orbit. And once they get into next orbit, they are pressurized to come back to their own place, and they will again come back to their own place. So this is how they jump into the orbits. So light is incident, they are getting energized, they are coming back, and then it is coming back. So this particular phase is called, they are getting excited here, and the second thing is they are getting emitted. So when the light falls onto the fluoropores, they get excited, and when they get excited, some light is also given out as an output of their excitation. So light falls onto the fluoropore, there is some light which comes out of the fluoropore as a energy. Energy is neither created nor destructed. It just transforms from one medium to another medium. That is how it is. So what happens? The light source is generating the light. It is falling onto this fluoropore. Once the fluoropore absorbs this light, it takes back the given light, and this is seen through the dichroic mirror, and then that is detected through the eyepiece. There is one more thing we need to study is, this is the visible light range. There are many waves. Even the infrared, which happens to be here, are waves, but we will not be able to notice with naked eyes. There is something here, UV rays, before this. So anything between 400 to 700 is visible. The wavelength I'm talking about, wavelength 400 and 700 is visible light. That is Vibgyor colors. But before that is ultraviolet, and after that is infrared. That is. So what happens? A fluoropore which is getting excited at 400 will always give you a wavelength of 500. Means excitation happens at one wavelength, and the emission happens at another wavelength. The another wavelength always has to be more than that. What happens? The more the wavelength of the light is less the energy. It is inversely proportional to each other. So what happens? It gets excited at 400, and possibly, just assume, it gives emission at 500. Though the number is more, the energy within that light is lesser. So we can say red light is having less energy than violet light always. But the phase, or that is the wavelength of red light, is always greater than the blue or violet light. So what happens when the same fluoropore can get excited with smaller wavelengths and also little more wavelength. So all those light wavelengths at which the fluoropore gets excited, this is called a spectrum of excitation. So even if it is wavelength is little less or little more or optimal is this one. This is highest excitation. That is called excitation light. But if the wavelength is little less or little more than the actual excitation, still the fluoropore emits some light. But that will not be the optimal. This graph, if we plot, it is coming as a spectrum. This is the excitation spectrum. Similarly, there is an emission spectrum. So if my light is getting excited at this level, the emission will be optimum and this will be. If my light gets excited at this, then it will be having emission at this. So these are the spectrums. We need not go more into physics. However, we can move ahead, and this is something we can study. Yes. The applications of microscope, if we will study, what we normally look into microscope is bacteria, parasites, the human and animal cells, cell division. Most of the fields, that is botanical, biological, crime investigation, educational field, and medical field. One important field I would like to discuss here, which we also internally carry a huge capability into cytogenetics. Cytogenetics itself uses bright field as well as fluorescence contrast types of microscopy. What happens here is, with the bright field, I remember Madam was discussing about cytogenetics into prenatal diagnosis of trisomy or the other issues. So what happens here is, my karyotype, I can have a karyotype after finding a metaphase. In bright field technique, what happens, of the culture is created, culture is produced, and in that, once it is laid onto the microscope, though it is not having stains. So what happens here is, I find a metaphase at 10x and then capture it at 40x, and then with the help of software I make it as a karyogram from the larger size to the smaller size, so that you can understand, the clinicians can understand what is the issue with this particular karyotype, what is getting repeated and what could be the cause and what has to be the treatment given. The fish also. So here all the chromosomes are being seen. So chromosome is normally bigger than the centromere. So what is centromere? Like center of the chromosome is centromere, the end of the chromosome is telomere. There are certain probes. If I am interested to study the parts of chromosome, first of all, chromosomes are very small, but though with the help of better microscopy we can see the metaphases, we can see the chromosomes. But again in that chromosomes, if we need to hunt for more details with naked eyes or with microscopes, it is difficult. So molecular probes are available which can directly hit to the centromere, telomere, or whatever area of interest you are looking for. They get attached to that, and with the help of fluorescence microscope we can hunt for them. The probes are in the form of fluoropores. Those fluoropores can be hunted with the help of fluorescence microscopy. This is one good application we would like to discuss. And karyotyping, as long as it is done, it is all bright field. But into fluorescence, you can have the applications into cytogenetics and hematology. It is into PGD, that is prenatal genetic diagnosis. I would like to, this is the last slide for mine. So what happens here is, repetitive strain injury. Repetitive strain injury while using the microscopes will be enormous. Like while using microscope, if I am moving my hand from focus to the knobs of the stage movement, maybe 1,000 or 2,000 times probably every clinician or every pathologist will move. But unknowingly, the strain is developed within the hands. It is not one part of hand, but also there is strain developed in the neck while continuous visualization. Eyes get also strained. There are multiple strains which we don't notify. Maybe in the old age only they will be notified. That happens normally whenever we are interacting with pathologists. They share the experiences. So there are strains developed with eyes and arms, neck, back, and the body posture. So what we have to do is, we have to consider the eradication features of this repetitive strain. So there are microscopes available. So normally a microscope is microscope, but a microscope which has this feature, that is repetitive strain injury, is better for us. Like similar like car is car, but somebody chooses a high-end car. Why? It is not just driving, but some other features also. Ergonomics at tubes, stage drive, focus, armrest, height adjustment, these are all ergonomics. It is considering the body posture, the human anatomy, to have the design of these particular parts. So in the earlier slides I was discussing, there are some tubes which will help to increase or decrease the angle within the tube. This is integrated module. Let us say I have a microscope which has not considered having the camera before. It is just binocular. Now I need to have a camera because my application needs camera now. Then we have something called as integrated tubes. Some of the microscopes can accommodate integrated tubes. With the help of that tube, I don't need to purchase a new tube, trinocular tube, but with the integrated tube, I can fix my camera also. Filters, that is DLF, blue filter, dark filter, these are which reduces the strains. Color correctness, flatness, we discussed during the objectives. This is automated intensity manager. Sir also was discussing yesterday, there are certain panes while we are using microscopy. Suddenly there is more light, whereas the others are not finding light. Only one person is getting more light. If there is automated intensity manager into the microscope, this can be reduced and you can have the better view and visualization and less pain while you are using the microscopes. Multi-view microscopes. Every single microscope is not giving you feature to have multiple heads of the microscopes. Only few microscopes will give you that capability because the light source has to be different for multi-view platforms. Camera options. There are multiple cameras, only for bright field and fluorescence, only for fluorescence, higher resolution, less resolution. Live cell camera and the ones which are for bright field microscopy are again different. So there are multiple cameras again. Flexibility for fluorescence filters. Some microscopes give you fluorescence, but they have only 2 filters, 3 filters, 5 filters, 7 filters. Based on number of filters you want to accommodate into fluorescence. Filters will help you to hunt for probes, that is fluorochromes or fluoropores. So based on that we need to design. So these are the multiple parameters which you need to consider while you are designing a microscope or you want to accommodate a microscope into your labs. No doubt we are there for you to help. You can always let us know if there is any opportunity for us to help you and assist you for any microscope opportunity. This was my last slide. Thank you very much for giving us an opportunity. We would love to work with you closely down the line. Thank you very much.